the tangent space to the tangent bundle at V, we can identify with a sum, a direct sum of two copies of the tangent space at the foot point of the vector. And we have some picture, some diagram of so this goes P, maybe I should put P in EM, and see, that's the projection. This is the derivative of the projection. This is the connector map. And this is projection. This is a composition of two projections. And then if we restrict to the unit tangent bundle, we have to restrict the second component to vectors that are perpendicular to V. And remember that the second component corresponds to sort of changing the vector part. And so if I have a vector V, if I want to move V inside the fibre of the tangent bundle so that the length of V stays constant, I have to move initially perpendicular to V. And so that's where that comes from. Okay. And then maybe I'll use the middle board. So I want to sort of draw two matching pictures. One is in EM, the other's in TM. So in EM I have a one-parameter family of geodesics. So alpha for each fixed S, alpha of ST is a geodesic. And the corresponding picture in TM looks, not surprisingly, very similar, except in this picture I have an initial curve V of S. Maybe V of 0 is some initial vector V. V in this picture is the vector V. And the point here is this is the geodesic flow for time t applied to V of S. So here we have orbits of the geodesic flow. And the link between the two pictures is that, so in this picture, if I look at alpha of ST, and then look at the tangent vector to that geodesic, this tangent vector is partial d alpha dt at ST. And that's going to be the same vector as V sub t, as the geodesic flow acting on V of S. So the curve of initial tangent vectors to our geodesics is the curve V of S. So the two pictures do match up. And if I look in the picture at the right, I get two pieces of, if I think of the Jacobi field J of t, which is partial d alpha ds at 0. Sorry, at s, no, I do mean at 0, comma t. So I look there, and then I look at the variation vector field, so with the eyes of a geometer. The corresponding thing that I see in this picture is, well, at time 0 here I see j of 0. Here I see the tangent vector to the curve v. So xi will be the initial tangent vector. And then if I flow along for time t, I get the derivative of the geodesic flow acting on xi. And, well, this corresponds to that, except that you only see half of the information in the left-hand picture. You need to, as well as j, you need to look at the derivative of j, which is the derivative with respect to t of d alpha by ds of 0t. And to match it up with what you see over here, you need to reverse the order of differentiation. So you want to think of this now as d by ds of d alpha by dt at 0t. And so if I look along this curve, partial d alpha by dt gives the tangent vectors to the geodesics, and that's the curve that you see by flowing the curve v in the picture over here. And then the idea is that if I think of d vt xi, if I decompose that into its horizontal and vertical components, the horizontal component is going to be partial d alpha by ds at 0t. That's the tangent vector to this curve, and it's the tangent vector to the curve of foot points. And then the second component is the covariant derivative of the vector field along the curve. The vector field is the partial with respect to t, and you differentiate in the s direction. And by reversing the order of differentiation, you can see that this is the same as the derivative of the Jacobi field. So that sort of matchup is kind of fairly fundamental especially when you try to think about dynamics of the geodesic flow. The dynamics really happens in this picture, but the geometry is based on the Jacobi field picture. Okay, maybe one more remark is I talked last time about orthogonal Jacobi fields. And so if I have, if I have a vector xi, I want it to be in the tangent space to the tangent bundle, but v, it defines a Jacobi field that I could call J for Jacobi field, and a subscript xi because it depends on xi, and the initial value of it is the horizontal component of xi. The initial derivative of it is the vertical component of xi. And so Jxi being perpendicular or being orthogonal to gamma that's equivalent to both xi h and xi v being in v perp. And geometrically, what this means is the fact that you keep xi v in v perp means that if v is a unit vector, you vary through unit speed geodesics, and having xi h in v perp means that you make your curve of initial points start off perpendicular to v, and you don't gain anything of geometrical interest by changing the speed of the geodesic or by sort of going at an angle, because you can just change the parameterization so that you go perpendicular. And so when you come to work with Jacobi fields, you nearly always are thinking about orthogonal Jacobi fields. Okay, so that's a summary of the kind of things or some of the things I said last time. And hopefully this correspondence between Jacobi fields and the derivative of the geodesic flow is clear. Okay, so now I want to talk about sort of, well, I guess I could say geometrical structures. So I could say well, I'm not sure whether they're on the tangent bundle or maybe it's on T here. So I guess the Riemannian metric is a structure on is that a structure on the tangent bundle of the manifold or the manifold? Anyway, so one of these structures is you can lift the Riemannian metric from EM to a Riemannian metric on TE. There are actually many, well, yeah, I think it's fair to say there are many ways to do this. There is a book. I can't remember the title of the book, but I'm pretty sure the author's last name is Yana, a Japanese mathematician. And this book discusses quite a few of these different ways of lifting the Riemannian metric, and has dozens, I think hundreds of formulas calculating all kinds, Christoffel symbols, curvature, all kinds of things for all of these different metrics. We're going to people who think about geodesic flow tend to focus on just one of these levels, which goes under the name of the Sasaki metric. And Sasaki wrote some papers in the early 1960s studying properties of this metric. I think the Sasaki metric probably predates Sasaki's papers, but he had to give it was convenient to give it a name, and his papers made Sasaki metric a natural choice of name. So what you do is very simple. If I have two tangent vectors in the same tangent space, I think I'll just use the inner product sign. We just have to remember to do the appropriate thing depending on what I stick inside the inner product sign. Well, you have horizontal components for your two vectors. We can take the inner product of them in the tangent space at P. This is the Riemannian metric from EM, and then you do the inner product of the vertical subspaces. So that's very natural. As I said, there are other ways of doing it. I don't actually remember any of the other ones at the moment. And so that's the Sasaki metric.
Any choice of affine connection would give you a splitting into horizontal and vertical.
That's true. So I could use, yeah, I think that may be one of the. But I think there were other things in the book, even based on the Levi-Civita connection. I honestly don't remember any of them. So I have always, in any calculations I've done, I've always thought of the Sasaki metric. So as far as I'm concerned, that's the metric on the tangent bundle. Okay, so we have the Sasaki metric. Now, the next thing is we have a canonical 1/5. So this is canonical given the fact that we have a Riemannian metric, because it's got the Riemannian metric built in it. So I will call it theta. I think the choice of letter is not canonical. Some people call it alpha. And what you do is you take the horizontal component of xi, and then you take xi, and this is meant to mean the projection from TTM to TM. So another way of writing this is you do the horizontal component of xi with V if xi is in TV TM. So obviously this has the Riemannian metric from M built into it. And then there is a symplectic form. Whoops, I do not mean theta, I mean omega. And so omega of xi eta is xi h with eta v minus xi v with eta h. I think it's that.
Define an almost complex structure, and it's just the J together with the Sasaki.
Yes, that's indeed. So, the sort of pair of things are related exactly like that. And now, of course, there is another possible way of doing this, which is exactly minus what I wrote here.
One of them will be d theta.
Yeah, indeed, one of them is d theta, but that's coming next. So it might be that what I've written here is minus what I should have written. So the lemma is true with the right choice of sign here. Okay, so maybe I will attempt to prove the lemma. And hopefully the science will come out right. And if they don't, well, or I can just stick plus or minus into the lemma. So I have to calculate d of a 1/4. So there's some formula that involve, so what I want to do is, maybe I'll draw a picture of what I'm going to introduce. So, work out, I could have a picture in TE. So in TM, I've got V, and then I want to have a two-parameter family or surface in TE. So I will have V of xt and V of 0, 0 is little v, and dv ds at 0, 0 is going to be xi dv dt at 0, 0 is going to be eta. So I have, and then there's a picture of the same thing in E. So alpha of st will be the foot point of V of st. So in EMU, you're then going to have a surface. And then I have the vector V, which there's absolutely no reason why the vector V should be tangent to this surface. This is just the surface of foot points of the vectors over here. And so I think I'll just leave the picture like that. You should imagine that from growing out of each point of this surface, so I'll put one more in. There is V of st. So we have, that's the picture in which I want to do the calculations. So so I have to work out d theta xi eta. So what I've got to do is, well, let me just write down. I'm going to do the derivative of theta of so I've got V, so V of st is a vector field. I could say we have vector fields along curves. So I don't know whether you have them along surfaces. Maybe I could say on alpha of st. And so when I differentiate, I'm going to use covariant derivatives along curves in this surface. So essentially I'm doing, when I do this d of the one form, I've got to have, what I end up calculating is d by ds of theta of dv dt. So this gives this gives eta, I think. This is differentiating sort of in the xi direction. And then I reverse the roles of s and t, and I take the difference. And there's usually a third term that involves the Lie bracket of two things. But I have deliberately set up something in which the Lie bracket is going to be 0. Not that I really have anything against Lie brackets, but if I do it this way, there's less stuff to write on the board. So we'll do it that way. And now you just start working out what all of this is. I'm differentiating with respect to s. Now, what is theta of something? It's the inner product of the vector with, you're at the vector v of st, and then you need where was the definition? I need the horizontal component, and that's going to be partial d alpha dt. So if I have, V, if I think about the curve V, if I think of V of st, and this sits over alpha of st. As I move v, the foot point moves, and the horizontal component is the derivative of the foot point. And I'm differentiating in the t direction, so that's why I have partial d alpha dt. And then, just by symmetry, the other term looks like that. And probably I should have put of st in there, but I'll skip that. So now I use the product rule for differentiation, and I'll sort of abbreviate things. So I'm going to get a dv s in a product with a d alpha dt plus v in a product with dds of d alpha dt minus dv dt d alpha ds minus v with d dt d alpha ds. Okay, now when I interchange order of differentiation here, I discover that this is the same as that. So those things cancel out. And then, of course, the idea is that what is left is hopefully going to be the same as omega. And if it isn't omega, it's going to turn out to be minus omega. So what do I have? I have dv by ds. That means I'm going in the s direction. Yeah, so at this point, let's work out things at 0, 0. So I'm going to get the vertical component of going in the t direction. So I think that's t direction is eta, isn't it?
But use the vertical product side. The first one.
Oh, sorry, yes. Sorry, I was looking at the second term. Yeah, I want the vertical component of xi. This one is going to be the horizontal component of eta. And now I get minus the vertical part of eta with the horizontal part of xi. And I appear to get minus theta. Okay, well I knew I was going to get one or the other. So now whether it's plus or minus doesn't make a lot of difference. Okay, so that's a calculation. Now, the one form and the symplectic form that I just showed you are probably more familiar as objects on the cotangent bundle. So on the cotangent bundle, you don't need any Riemannian metric. This just comes, once you've got E, you have this. You have the canonical one form. So if I have, what you do is if I have, what's a good letter for a covector?
V star.
V star. Sounds good. So I just take, so I want to have xi in the tangent space to T star in at V star. And what I do is I can take V star and apply it to the derivative. I've got a projection from T star EM. So I can take the derivative of that projection, apply that to xi. Now, this gives me a vector at P, and V star is a covector at P. Covectors exist to act on vectors and give you a number. So there it is. And the form that we have up there is this one, except that there's a correspondence between the tangent and cotangent bundles given by the Riemannian metric. And the correspondence is if I've got the vector, if I have a vector V, what is the corresponding covector when you do in a product with V? This is the relationship between the gradient of a function. If you have the derivative of the function is the covector, the gradient of the function is that covector turned into a vector via the standard inner product on Rn. So, and then it's very clear that our canonical one form up there is just this one transported over to Tn. So some people like to do their geodesic flows on the cotangent bundle. I'm not one of those people. So now, if I've got to do geometry, I can't do. So I work with the tangent bundle, and then of course the once you have the one form, you can do d of it, and d of you get the same relationship here as we've got for our vectors there. So these objects are standard objects in symplectic geometry, and they've just been sort of translated from T star to Tm by the Riemannian metric. So of course, different Riemannian metrics give you different canonical forms on the tangent bundle. Okay, so that is our symplectic form. And now, the reason for mentioning this symplectic form and the one form is that they've got a lot to do with the geodesic flow. So the first thing so the geodesic flow is a flow on the tangent bundle. So there has to be a vector field on the tangent bundle. So maybe I'll call that G of V for geodesic. Well, I think I mentioned already yesterday that the geodesic flow vector field is given by that. Because that says, well, if I draw a picture of my geodesic V, gamma V, tangent to V, the curve of foot points has initial tangent vector V, so that's why you see a V there, and the d by dt of gamma dot equals 0. That says you have a 0 there. So that's the geodesic vector field. And now G is a Hamiltonian vector field. So the idea of Hamiltonian vector fields is that you have a symplectic form, which we do, and then you have a function. Hamiltonian function. And our Hamiltonian function, or the one that gives us the geodesic flow, is to take half, I think I want the half, the norm squared of the vector. This is the energy. Well, when you integrate it, when you do the integral of this thing for the tangent vector along the curve, you get the energy of the curve. And so I think if you think of V as the velocity, the particle that's moving, this is with unit mass, this is the kinetic energy. So we have that. And now the idea of the Hamiltonian vector field is that dH is a one form. And so dH is meant to be omega with, so dH of some xi is meant to be omega of, so xi being of course into VTN. You're meant to get dH xi equals omega GV xi. But I will put plus or minus in front because I can't remember what order I'm supposed to have things here. I also can't really remember whether my omega is plus or minus the one I've got there. And with the correct choice of sign, it works out. And so the point of, so it turns out that let's verify that this works up to my possibly incorrect choices of sign. What is dH of xi? Well, I start varying the vector v, I go off in the xi direction. Moving the foot point doesn't affect things. It's the vertical component that we need. And there's going to be two terms that are symmetrical that will cancel for half. And what you get is V with the vertical component of xi. So actually you get a half of this plus the same thing with the order reversed. And then if I take omega and plug G and V and xi into it, I'm doing omega of V comma 0 xi V, xi H xi V. And now I think my definition of omega says that I do inner product of first component here with second component there minus second component here, first component there. So I think I have plus here. So we do have a Hamiltonian vector field. And so Hamiltonian vector fields are very, very much studied. And there's a lot of general theory. And so you can explain, saying that we can explain a lot of the properties of the geodesic flow by saying that they're the properties of Hamiltonian systems. So now I don't think that explains anything. What it means is that Hamiltonian systems are a generalization of the geodesic flow. And so if you if you're familiar with the geodesic flow, that helps you understand Hamiltonian systems. I think for me it works that way around. Yeah, sort of geodesic flow, but well, more or less geodesic flow. Okay, so one of the things that happens is that, well, when you do the geodesic flow, the Hamiltonian function is preserved. That amounts to, in the geodesic flow terms, that means that geodesics go at constant speed. The other property that's standard is that the flow preserves the symplectic form. And so you can do a calculation using Cartan's formula. It's very short, and I usually find it tremendously unilluminating. So last time we did a calculation. Oh, actually, maybe I should say there's something obvious that I think I haven't said yet, which was that. What's that?
There's a picture for Cartan's form.
Ah, well, maybe that's illuminating. But, you know, yeah, last time we had y and z were two Jacobi fields along geodesic, and we wrote down something that looked like y, but we wrote down y z prime minus y prime z. And if you think about the symplectic form, which, it's still on board, and you think about if you think about xi being the pair y of 0, y prime of 0, and eta being z of 0, z prime of 0, that will mean that this means that y is the Jacobi field associated with xi, and z is the Jacobi field associated with eta. What you can see here is that if I plug in 0, what I'm going to get is xi and eta plugged into the symplectic form. And at time t, what I get is the derivative of the geodesic flow for time t acting on xi and acting on eta. So I've got the symplectic form. And last time we differentiated this and discovered that you get 0. So that this is constant. So that the fact that this stays constant, that is exactly the statement that omega is preserved by the geodesic flow. So this isn't just a random choice of thing to look at. It's this canonical symplectic form. Okay, now one advantage of involving the symplectic form and observing that it's invariant is that allows us to explain why we have an invariant measure. So I think this board could go. So if omega is a symplectic form, well, actually there are two ways you can go about creating a measure. Okay, yeah, well, one of them is if omega is a symplectic form. On a 2n dimensional manifold. Omega to the n defines a volume. So what I mean by omega to the n is if I have xi1 eta 1 up to xi n eta n, I think what you do is the determinant, and you take the determinant of omega of xi I. The typical entry is omega of xi I with eta j. I think that's the formula. There's another way of defining a volume. If we have an inner product, well, if we have a Riemannian metric, then we can define volume. Basically, all you've got to do is you just decree that if xi1 eta 1 up to xi n eta n is orthonormal, is an orthonormal basis, then they span a what's the thing that they, the cube-like thing that they span, what's the word for that? They span about a hypercube of volume 1. So that gives two different ways of defining volume. And so the idea is that both of these ways of defining one thing we could do is we could take the Sasaki metric, take the volume, the notion of volume that it defines, and I claim that that notion of volume is the same as the one defined by the canonical symplectic form. And so the way to see it is to make the right choice of the xi's and etas. All I've got, both ways of doing things amount to saying that you've got your tangent space and then you pick some hypercube in it and decree that this hypercube has volume 1. Once you've made that choice, you've defined volume in that tangent space. So the choice of xi and eta that you want to make
generally, if you have a triple symplectic form, inner product, and almost complex structure, compatible triple, then both will get the same.
Yeah. So, and I think what I'm about to show is how you see it in general. You just pick the right basis. So I want to pick xi I. First of all, I want to pick E1 up to E. I want to have, suppose V is in T, P. I want to pick an orthonormal basis for T, PM, and then I want to pick xi I to be EI, 0, and eta I to be 0, EI. So if I do that, it's obvious that these things are unit vectors in the Sasaki metric. It's obvious that the inner product of these vectors in the Sasaki metric is 0. It's also obvious that if I take either of them for I and either of them for j, that the I1 and the J1 are orthogonal. So that gives me an orthonormal basis. And then you can just figure out what omega does to these things. And if I have an I and a J, for I and J different, you're just going to get 0, because the EI and the EJ are orthogonal to each other. And omega of xi I, eta I works out to be EI minus 0, 0, you get 1. And then if you look at the determinant that I talked about, you're just going to get 1s on the diagonal and everything else 0. So the volume, the two notions of volume are the same. And then the fact that the geodesic flow doesn't change. Omega says that if you think of the volume as coming from the symplectic form, it's preserved by the geodesic flow. So that's why we have the natural invariant measure. And this measure goes under the name of the Lingerville measure. Okay, there is one sort of detail that I've left out, which is that this is the measure for the whole tangent bundle, and we usually think of the geodesic flow on the unit tangent bundle. And I think I will be sort of lazy and not do all the things for the unit tangent bundle. But if you think about what happens if I have the full tangent bundle, you can look at the tangent bundle of vectors of different lengths, and the geodesic flow is basically the same on all of these things. If I have a unit vector v and it's rescaling of length r, you just see the same geodesics. You just go along this one faster. And if you just take the volume on the unit tangent bundle and sort of
theta.
Yeah, so I think I can use theta.
Theta
Although
is d theta to the n minus 1.
Yeah, so I think actually if I take
theta with d theta to the n minus 1.
yes, that does it. Although then I really have to prove, I would have to go to the trouble of proving that theta is also invariant under the geodesic flow, which it is. And I think what I can do is if I take omega, if I have a unit vector v, I can just take, I think I can take the pair sort of v 0 and 0 v, plug them into omega, and then take things orthogonal to v. I think that does it. But anyway, so you can restrict, if you sort of restrict to the unit tangent bundle in the right way, you get an vary and measure. So I think I won't worry about the details there.
Though omega won't be a symplectic form and restricted to maybe 10.
Right, omega, yeah. Well, because you, but omega essentially, well, omega is a symplectic form. What happened, and one of the reasons why you think about orthogonal Jacobi fields in preference to all Jacobi fields is that so omega is symplectic on orthogonal Jacobi fields. So if I've got my vector v in T1 and M, the orthogonal Jacobi fields correspond to this direct sum. This is dimension twice n minus 1, and omega is a symplectic form on this space. So, and then you've just got the tangential stuff, which doesn't really, it doesn't matter.
It's only generated on the kernel of theta.
Yeah. Or you can always just think about the whole tangent bundle.
Theta is very.
I think there must be, but I didn't.
The real vector field. Theta is a contact
Yeah.
form. So contact form defines a unique real vector field, and the geodesic vector field is the real vector field.
Yes.
Which preserves the contact forms.
Right, but there's some calculation that I didn't remember this morning, so. I think one way of defining the volume would be I could think about all vectors with length less than or equal to 1. And if I've got some subset in the unit tangent bundle, I can just take the sort of cone going into the middle. That will flow along. And then you can just define the volume of that set to be the volume of the cone. That would be one way of doing things. Okay, so I think I actually want to keep this in mind in what I'm going to say next. Yeah, so I think I've said those things. I want to say some things about nice families of Jacobi fields. And I'm only interested in orthogonal Jacobi fields. So pretty much Jacobi field means orthogonal Jacobi field. So there's a geodesic here. And in this picture I want to think actually of M as being 3-dimensional. And there's a sort of nice way in which you create a 2-dimensional family of orthogonal Jacobi fields. And what you do is you think of a surface that is perpendicular to your geodesic. So, yes, there's a piece of surface. I really only need the germ of the surface, a small piece of surface around the point on the geodesic. So it's going to be I can move that up, that's nice. So it's a surface orthogonal to gap. And now my surface, since I'm in this picture, dimension M is equal to 3. And if I had if the dimension of M was not equal to 3, what I would be looking at is a hypersurface with codimension 1 that is orthogonal to the geodesic gamma. So the picture in the case of if dimension of M is equal to 2, the picture is I just take a curve perpendicular to the geodesic. And now I can take unit normals. I can vary gamma through geodesics of the form gamma sub V, where V is a unit normal to S. And obviously it's got to point on the same side of S as gamma dot of 0. So if I do that, I get a sort of 2-parameter family of well, in this case I get a 2-parameter family of geodesics that are variations of gamma. In the surface case, I get a 1-parameter variation. And in the general case of an n-dimensional manifold, I get an n-1-dimensional family. And then, actually, maybe I don't want to use V there. Maybe I'll use U, because it's a unit normal. And now if I pick a vector V, that V in the picture is meant to be tangent to S. So V is a tangent vector at the point gamma of 0, which is the point where gamma goes through S. So if I have a vector V tangent to S, there is a Jacobi field. Associated to V. Well, and S. So what I do is I've got my vector V, and then inside S there is going to be a curve tangent to V. So this is a curve in S tangent to V, and then I look at the geodesics coming out of that curve that are perpendicular to S, and then that's now a 1-parameter variation, and I take the associated Jacobi field, and that gives a Jacobi field. And if I take different curves in S, as long as they're tangent to the same V, I'm going to get the same Jacobi field. So that gives in the case of our 3-dimensional manifold, we get a 2-parameter family of Jacobi fields. In the case of a surface, we just get Jacobi fields. And in the case of, if the dimension of n is equal to n, we get an n-1-dimensional family of Jacobi fields. So, and this construction is natural, and pretty much all Jacobi fields that you're interested in thinking about arise as members of such families. So one case is I could take Maybe I should draw it as a disc. I can take the geodesics through gamma of 0 that are perpendicular to gamma. And then I take geodesics orthogonal to those geodesics. That would be one way of setting this up. And then in that case, what you get is you get Jacobi fields J sub xi, and xi would look like v comma 0. Maybe I could call it. Maybe I'll use W for this letter here. Because I've often used V for the tangent vector to the geodesic. So that's one version of the picture. Another version of the picture is think of all of the geodesics that start at gamma of 0. Okay, at gamma of 0 you don't see any hypersurface. As soon as you go down the geodesic you do. And the hypersurface that you see is sphere centered at gamma of 0. So, and in this case, the Jacobi fields that you're going to be looking at will be J xi, where the initial data is 0 and the initial derivative of the Jacobi field. So they're the two main cases. Well, they're probably the two main cases. Another case also you could think about horospheres. That's the other important case. So if I have my geodesic, there's gamma of 0, I go at gamma of t, I draw the sphere centered at gamma of t, and then I let t tend to infinity, and I end up with horosphere. The spheres, there's an easy calculation using the triangle inequality which says that these spheres get bigger, and then you take the geodesics perpendicular to them. We saw this construction in the first lecture. So that family of Jacobi fields, by varying through these guys, has this form. And that pretty much covers all Jacobi fields that you ever think about. Okay, so these are good Jacobi fields. And now there's a sort of formula for, well, if we have the surface S, and then I have a curve in S tangent to W, and then I look at the normals to S along the curve W. So the initial data for our Jacobi field is W, comma, whatever you get. And what you're doing is you're taking the, well, yeah, I've got this, these are the initial tangent vectors to the geodesics, which then go off. Then you form the Jacobi field and you differentiate the Jacobi field along the geodesic. But if you reverse the order of differentiation and differentiate, if you think about the derivative in the geodesic direction first, that gives you the unit normals, and then differentiate this way second. That means that you're, yeah, so if I have J, if I look at J prime as 0, so I've got, yeah, I should draw it. Let me draw a picture here that I have a variation alpha of ST. T goes this way. S is the parameter along the curve of the surface. W is partial d alpha ds at 0, 0. Gamma dot of 0 is partial d alpha dt at 0, 0. And J prime at 0 is partial d dt d alpha ds at 0, 0. And I want to think of it the other way round. I reverse the order of differentiation and get dds d alpha dt at 0, 0. And when I look at this, what I'm doing is I'm looking, this is the curve of unit normals to the surface with foot points along the curve in the surface, and then I do the covariant derivative. And this is a standard operation in differential geometry. This is the second fundamental form. It's the second fundamental form of the surface. And I think another name that's used is the shape operator. So this is a quadratic form that describes the surface up to the sort of first order description of the surface is the tangent plane. This is the next level of description. And this thing, this shape operator is so you get what you get is you get a symmetric linear map. So gamma 0 per is the tangent space at gamma 0 to the surface, and the symmetric linear map is from gamma 0 to its and so, so you get this symmetric linear map. So if I now think about some vector v, and the geodesic gamma v, and then I look at v per plus v per as a space of possible initial value or derivative for a Jacobi field. My construction over here is going to produce what you get is you get n-1 dimensional subspaces of this, and they're subspaces of the form. You get the graph of a symmetric linear map from V per to V per. So this is the class of n-1 dimensional subspace. So an n-1 dimensional family of Jacobi fields is just amounts to picking an n-1 dimensional subspace of this 2n-2 dimensional space. And the distinguished ones that we've picked out are the ones that are the graphs of linear maps, of symmetric linear maps. And what that means is that what we have picked out are the graphs of the symmetric linear maps.
These Lagrangian subspaces.
Exactly. The Lagrangian. Which I'm cheating slightly when I say the graph of a symmetric linear map. Because if I look at the case of the Jacobi fields that are initially 0, you don't have a linear map. But as long as your initial values are all non-zero, you get the graph of a symmetric linear map. And then you've just taken the sort of closure or something. And if And if you're at a place on the geodesic where some of these Jacobi fields vanishes, you can just move a little bit to where they're not vanishing. And then you get the description as the graph of a symmetric linear map. And these are exactly the Lagrangian subspaces of V per plus V per. And what this means, so this means that if I take, so if Y and Z are obtained from the same surface S, you're going to get Y Z prime minus Z Y prime equals 0. And if you think about the fact that you've got this shape operator and it's symmetric, then it's almost immediate. It's immediately obvious that you do get 0, because if Y of 0 is W, maybe W1, Z of 0 is W2, Y Z prime is going to be W1 times, say, so L is the shape operator. I get that, and if I do Y prime Z, I've got L W1 W2. And symmetry of L means these are equal. So when you take the difference, you get 0. So you get these Lagrangian subspaces. And so, of course, in the case of a surface, you just get one-dimensional subspaces, which are all Lagrangian. So somehow the right generalization of Jacobi field in a surface to higher dimensions isn't Jacobi field. It's one of these Lagrangian subspaces of Jacobi fields. And the shape operator basically describes the subspace for you. So once you know the shape operator, you know the subspace. And so let me finish by going back to the Jacobi equation and talking about how this sort of thing evolves. So I think I want to think about surfaces. At least initially I want to think about surfaces. So in case of a surface, I have a geodesic gamma, and then I vary gamma through geodesics. And well, I've really just drawn the picture that defines a Jacobi field. And then I want to add to the picture the curves that are orthogonal to the family of geodesics. And so if my geodesic in the picture is J, sorry, my Jacobi field is J, what you have is that J prime xt is the shape operator for maybe S sub t is the shape operator for the relevant curve applied to J of t. Well, except when J of t is equal to 0, which I won't worry about. And now the shape operator for a curve this is a linear map from a one-dimensional, the orthogonal direction to itself. It's a linear map of R1. It's a number. The number is the geodesic curvature. So this is the geodesic curvature of the curve orthogonal to gamma. So as my picture evolves, the curve perpendicular to the geodesics evolves, and you want to see how the geodesic curvature of it is changing. So let's define U of t to be geodesic curvature of this curve at time t. And then U of t is j prime of t divided by j prime of t, except when I'm trying to divide by 0, in which case I just don't. At that point, the curve does something singular, such as when your family of geodesic circles collapses to a point. Anyway, and so there is an advantage thinking about U rather than the Jacobi field J. Well, there often is, which is because if I take the Jacobi field J and just rescale it, if I double it, I've got essentially the same Jacobi field. And so the scale factor cancels out here. So sort of different U's correspond to genuinely different Jacobi fields. Anyway, if you take this and the Jacobi equation, I'm thinking about orthogonal Jacobi fields. And so I can write my orthogonal Jacobi field J of t, just little j of t times a unit normal, which that will just be the unit tangent vector to the curve perpendicular to the geodesics. And so the Jacobi equation boils down to j double prime of t plus the curvature of gamma of t times j of t equals 0. And U of t is j prime of t divided by j of t. And then it's easy to see that the differential equation satisfied by U is this. If you just take U, differentiate it. So U prime of t is j squared. I just get j double prime minus j prime squared. So this is j double prime over j minus u squared. I think that's right. And j double prime over j from the Jacobi equation is minus k. Yeah. So you get this equation. And this is a Riccati equation. It's a special case of the Riccati equation, but you get an equation like that. And if you wanted to study if you want to sort of build surfaces in which geodesics do things that you want them to do, or if you want to kind of control the behaviour of geodesics in a surface, usually you end up thinking about the Riccati equation. It's very, very helpful. Okay, so that is the Riccati equation. And now, in the case of surfaces, there is a higher dimensional analog. There's a higher dimensional Riccati equation. And what you do is you think of your geodesic in higher dimensions, and then you pick an orthonormal basis for the orthogonal complement, say E1 up to En minus 1, and you parallel translate that along the geodesic. That's actually what En was in the discussion about surfaces. And then you you sort of use coordinates based on this. And you think about the matrix U of T. So the columns, you can think about the Jacobi fields J1 up to Jn minus 1. They should be associated to the surface S, and you have Ji at 0 is Ei. You can write your shape operator will be a symmetric matrix. So U is the shape operator, and you get an n minus 1 by n minus 1 symmetric matrix. And then you do the same, you appeal to you look at what the Jacobi equation. So if you do the calculations, you get the derivative of U plus U squared plus the sum of the matrix is equal to 0. This matrix is symmetric, and it's n minus 1 by n minus 1. And the ijth entry at T is, so let me use capital N to denote the parallel vector fields. The ijth entry of this matrix turns out to be the inner product of the curvature tensor with EIT, gamma dot of T, gamma dot of T with EJ of T in it. There should be, and yeah, you get that. So the diagonal entries in this matrix have EI, EI, and this is unit vector, orthogonal unit vectors. So the diagonal entries of this matrix are sectional curvatures. The other entries are not sectional curvatures. They're whatever they are. But what you can do is you're free, for any given time, you're free to pick this basis in such a way that when it arrives at gamma of T, it's doing something nice. And so you can take, this is some symmetric So if you pick the right basis, you can diagonalize this symmetric matrix, and then you'll just have a matrix of sectional curvatures. Of course, the basis that makes it diagonalizes at one t is usually not the same as the one that works at another t. But you can get the idea that if we have negative sectional curvatures, that we've got a negative definite symmetric matrix here. And of course, in the surface case, if we have negative curvature, we have a negative number here. Okay, well that's a good place to finish at. But this higher dimensional version of the Riccati equation it fairly much allows you to think in higher dimensions in the same way as you do for surfaces. So let me finish there.